Hello, this is Mr. White, and this video is on the Intermediate Value Theorem, also known as the IVT. And IVT is an acronym that you may use not only on my assessments, but also on the AP exam itself. IVT is universally recognized to mean Intermediate Value Theorem. So here are the two exercises we're going to do in this video. Honestly, the IVT is something that supports more interesting theorems that come up later in calculus, but when you are asked to actually use it directly in an exercise, it typically looks like something like what you see on the screen here. So there are the times as well that the exercise will appear in this video. But let's first start with this. This is typically a challenge that I give to students when I'm introducing the IVT in a classroom. And I ask students to draw a function that is continuous on the open interval from A to B and passes through the two red points, but does not cross the line y equals k. And students often assume that this is one of those problems where I pull out the rug from underneath them later on and go, haha, it's not possible. Well, no, this one is possible. And I encourage you to pause the video and see if you can come up with the correct solution before I tell it to you. Now, typically when I throw this out there in class, it starts off with a few somewhat joking suggestions where typically there'll be a student who says, why don't we do something like this? And I trust that the student knows that that's not really a valid answer for two reasons, really. Number one, it's not even a function, right? This doesn't pass the vertical line test. And furthermore, we understand that this green dashed line with two arrowheads at each end, we know that that really represents a line that is infinitely long, and therefore you can't really go around it like I have shown here. All right, so what might come later is that, again, another sort of joking suggestion. There may be a student who somewhat cleverly says, can I do that? Again, we know that this dashed line doesn't really have discontinuities in it, so we know that's not really a valid answer. Now, one answer that is not really what I'm going for here, but I have to admit, I would have to accept if it were on a test, is that every so often there'll be a student who will say, why can't I start at this point and continuously jump out of the screen, and I can't really show this on this two-dimensional board here, but jump out of the page in three-dimensional space, hop over the green line, and land back on this point. And I have to admit, if this were on a test and I phrase the question as you see here, I would have to give that credit because there's nothing that explicitly states in this problem that we're dealing with two dimensions, right? So I'd have to say, okay, that's my fault for not saying we're dealing with a two-dimensional problem. So I like that, and in Calc 3 typically is when you start getting into really delving into three-dimensional space and the calculus of three-dimensional space and functions. But I will say that throughout this entire course, with the exception of a few topics at the very end, we will be assuming that we're talking about two-dimensional problems here. So how does one complete this challenge on the implied two-dimensional plane? Again, here's your last opportunity to pause the video and see if you can come up with it. If you'd like a little bit of a hint before I tell it to you, I'd say really focus carefully on the wording here. And in particular, think of what the implication of this is. Open interval with parentheses A, comma, B, close parentheses. It's a mistake in calculus to think that we can gloss over these words and that they're there just to be ignored. That has some significant meaning there. So here it is. Here's the way we could accomplish this. How about that? Take a look at that and notice that that does satisfy the challenge because this function only needed to be continuous on the open interval. In other words, it only needed to be continuous for all the points between A and B, but it didn't have to be continuous at x equals A and x equals B itself. So again, that's how the challenge is completed. And notice that what we have here, there's a discontinuity at B, but the parentheses say it didn't have to be continuous at B. So there it is. Now let's go ahead and amend this problem then and say, okay, well done. But what if we said closed interval now? And again, my message to you is don't gloss over open intervals versus closed interval. That sometimes is a very key point to be aware of. So what about the closed interval where I put bracket A and B closed bracket? Now that preceding solution doesn't really work anymore, because now I have to be continuous at b, but clearly in this picture I'm not continuous. This function is not continuous at b. So I'm not going to challenge you. I'm not going to ask you to pause the video and ponder this one. I'll go ahead and reveal that that is impossible. You cannot draw a function that is continuous on the closed interval without crossing the line y equals k. And that's really what the intermediate value theorem states. So let me bring its formal statement up here. The intermediate value theorem states that if f is continuous on the closed interval from a to b, including the endpoints a and b, and if k is any number between f of a and f of b, then there's at least one number c on the interval from a to b such that f of c equals k. So that's a bit of a mouthful, I acknowledge. Let's make sure we completely understand all the implications of that. All right, scroll down a little bit here. So where are f of a and f of b in this problem? Well, a and b are x values, and f of a and f of b are their respective y values. So I always encourage you to draw sketches like this to really envision what these wordy theorems are talking about. And we see that k is a number on the y-axis that is between f of a and f of b. And if we are going to draw a continuous function that connect those 2 points, the intermediate value theorem states that there is at least one number c on the interval from a to b, then again, those are x values. There's at least one number c where f of c equals k. And in this case, the way I've drawn it, here is where c would be on the interval from a to b, and we see that f of c does equal k in this picture. Now, focus on the word at least as well. There's nothing that says you can't have more than one c value. So let's go back to, let's see, that point. And, there's nothing to say you can't cross it more than one time. And in that case, we might say, okay, there's 3 c values. And I might call that c1, c2, c3. And we see that in all 3 cases of those c's, I'll put f of c subscript I to denote that there's multiple c values. And we'll say that f of c sub 1, f of c sub 2, f of c sub 3, all 3 cases, f of c equals k. All right, notice that the intermediate value theorem is our first example of something that's called an existence theorem. And what that means is that it simply guarantees that something exists. So the intermediate value theorem, the IVT, guaranteed that this number c, at least one number c, would exist on this interval that satisfies these conditions. Yet it doesn't tell us how to get that value c. So that's just something to be aware of. As far as how do we actually find out what c, and if there's multiple values, how do we find out what all the values c are? Well, you're going to rely on various algebraic techniques and or graphical techniques. But the IVT simply guarantees that it exists. It doesn't tell you how to find it. So, all right, let's go ahead and look at these exercises here. And this first exercise wants us to explain why the function has a 0 in the specified interval. So here's a function f of x given to us. It's a cubic function. And we need to guarantee that it has a 0, aka, remember, a 0 is another word for an x-intercept. We need to guarantee that it has an x-intercept or 0 on the interval from 0 to 1. All right, well, let's start by before you even jump into thinking IVT, you have to guarantee that you've met the conditions on which you may apply the IVT. So what I mean is that if you're dealing with, let's say we're dealing with the function tangent of x. That is a function, and let's say is on the interval from 0 to pi. Well, that is a function that looks kind of like this. And we see that that function is not even continuous. So you're not allowed to try to even try to apply the IVT if it's not continuous. Remember, the IVT only applies to continuous functions on closed intervals. Okay, So let's go back to our original cubic function, and I would start by noting that this is a polynomial. Remember, polynomials have either constants and or linear terms and or quadratic terms like x squared, cubic terms, etc. They're basically whole number powers of x. If you have like x to the negative 1 in there, it's no longer a polynomial. If you have x to the 1/2 power in there, that's not a whole number, not a polynomial. But this is a polynomial, so I would, and all polynomials are automatically continuous. So I would say, since f of x is a polynomial, it is continuous not only on the interval. Again, all I really have to guarantee is that it's continuous on this interval, but it's an even more powerful statement, if applicable, to say that it is continuous everywhere. That covers the interval as well as all other x values. So it's continuous. You have to state that. And then we have to look at the endpoints. So let's see what happens at x equals 0 and x equals 1. F of 0, if I put a 0 here, 0, 0, I see that I'm going to get negative 2. And what about f of 1, the other endpoint? If I put a 1 in there, I get 1 cubed plus 3 times 1 minus 2. That's going to give us positive 2. Let me do that. Okay. So since those conditions occur, and a 0, again, we're looking for a place where when we say there's a 0, we mean we want a c value where f of c equals 0. And notice that 0, or f of c, is between these two. So I might put, and I know this is not the best English, but this is not an English test, it's a math class, so I'm just getting all the facts here. And 0 is between f of 0 and f of 1. In this case, it's greater than f of 0, and it's less than f of 1. So since those conditions occur, the IVT, and again, I am allowed to use that acronym, that at least one value of c on the interval such that, and I'm just going to get this in without running out of space, such that f of c equals 0. So here is my solution. I don't need to find out what c is. I only need to guarantee that it exists, that it satisfies those conditions. I will go ahead and show you that if you are so inclined on a calculator, you could graph it, and you could see that between 0 here and 1 here, we do see that there's some c value between 0 and 1 where there is an x-intercept, or a 0. But I don't even have to find it. All I was asked to do is explain why the function has a 0, and I've done that. All right, let's look at the other type of exercise here. So let me get this out of the way and drag this up here. Again, kind of similar in concept, and in this case, I'm asked to verify that the IVT applies to the indicated interval and find this time we're actually asked to find the value of c. And again, the IVT itself isn't going to help us with this task, but I invite you to pause and try your hand at least the first part, verifying that the IVT applies. I'm going to go ahead and do it right here, but I'll again invite you to try it yourself and compare answers with mine. So again, what do? We start out by saying, since f of x is a polynomial, it is continuous. Therefore, again, in stating that it's continuous everywhere, or at least on the interval from 1 to 5, but continuous everywhere is just a more powerful statement there. That's what opens up the door to try to apply the IVT. So since f of x is a polynomial, it is continuous everywhere. And since, let's see, f I'm going to check the endpoints, f of 1 and f of 5. If I plug a 1 into the function, I get 1 cubed minus 5 times 1, that's negative 4, plus 6 times 1, that would give us a positive 2, right? And what about plugging in 5? F of 5 equals 5 cubed, that's 125, minus 5 times 5 squared, that's also 125, plus 6 times 5, that's 30. I want to point out here, let me give a quick plug to mental math. Again, just because I allow you to use a calculator and I insist there are times where it's appropriate, I will also insist that there are times where mental math is the way to go, and we'll get you there much more quickly and efficiently. So, there are two endpoint values, and notice that in this case, we don't know if there's a 0 or not, but notice in this case, we weren't asked to find a 0. We're asked to find where f of c equals 8. So really envision what that's asking us to do. We know that f of 1 equals 2. So here's 1, here's 2. We know there's a point there on the function. We know that f of 5 equals 30. So here's 5. And I'm not too concerned about drawing a perfectly scaled drawing here. I just want a very conceptual sketch. And again, we're not looking for a 0 necessarily. There may or may not be a 0. If it looks like this, there's not a 0. If it comes down and does that, then there is a 0. But again, we're not interested in a 0 so much as we are a value where the function equals 8. So let's put an 8 there. And again, really recognize that this is where the IVT applies, that I cannot get from one point to another point without crossing that line. Okay? So what do we do here? We basically demonstrated that the IVT applies. So since f of x is a polynomial, it is continuous everywhere. I see those two values. And so to just really complete this thought here, let me extend the page a little bit and finish this sentence. And let's see, 8 is bigger than f of 1, but less than f of 5. IVT, I'm going to write it slightly differently, guarantees a value of c on the interval from 1 to 5 such that f of c equals 8. And that completes part 1 of the request. I've guaranteed that there's a point where f of c equals 8. Now, what is that value? It really just comes down to in this case, I would say just kind of guess and check. And in this class, if it ever comes down to guess and check, it'll be fairly simple. You won't be having to look for very ugly, irrational solutions if you're given a cubic. In this case, I'd say let's just try the integers, f of 2, f of 3, and f of 4. Those are the three integers on the interval. And let's see if any of those give us our f of c equals 8. So again, little mental math here. F of 2 is 8 minus 20 plus 12. So 8 minus 20, negative. That's going to give us 0. So it turns out there is a 0 on this interval after all, even though that's not what we're looking for. What about f of 3? That's going to give us 27. Minus 45 plus 18, well, that also equals 0. Kind of makes sense. I can see how if I actually cross the x-axis, it seems like I'd have to cross it again in order to get back to my point up there at f of 5. So f of 4, fingers crossed. Let's see what this yields. F of 4 equals 4 cubed. That's going to be 64 minus 5 times 4 squared, that's 80, so we're at negative 16, plus 6 times 4, and that brings us up to 8. There it is, that's what we were looking for. We have found the value where f of c equals 8. So, to complete the picture that I was developing earlier, I can assume that the polynomial does that, and I see that at f of 4, we get our y value of 8, and here's my complete solution. In green, the verification of the IVT. In blue, the development of the C value that satisfies the IVT. And if you like, here is a calculator verification of our work as well.